Here, set up my screen here nice and big. So this lesson is on our first lesson on forces. And forces are important because they cause acceleration, and acceleration is important. So you probably learned in elementary school that forces are a push or a pull, and that is still true today in high school. So what we'll study though, we'll study specific kinds of forces and learning how to calculate and understand what these, gravity, normal, friction, applied, and tension actually mean. Specifically, like really the first three. The other two are actually more general terms than you might think. But really all that matters when it comes to forces, are they balanced or unbalanced? Because if they're balanced, they will, you will have a system of either uniform motion or no motion, which, for example, if you were designing a bridge, balanced forces are a really good thing. Unbalanced forces, of course, are really good if you're designing a vehicle because you want that thing to move. So understanding unbalanced versus balanced forces is really important, and what makes that happen or how you can control that. Yep, so balanced forces make things stay still, and unbalanced forces make things move, or specifically accelerate. Because you can have a uniform motion, like constant velocity, with balanced forces, but you can't have an acceleration. So you can't start something moving without an unbalanced force. Okay, so before we really get into the calculating forces, there is these Newton's laws of motion, and Sir Isaac Newton, he calculated or he determined so many things. He would have been like mid 1600s, and they said he spent a lot of his life. I'm not sure why. I can't remember if there's maybe some disease going around or something, but he's a rich man, and I think he spent a lot of his life basically in solitary, living sort of on his I want to say a resort, but not quite resort. He's from England, but wouldn't have been a resort, but whatever he had, his farm, his home, his rich home with all his servants. And he came up with some unreal things. Isaac Newton just, gravity is, we'll study gravity later in the course, and of course he came up with the formula to describe gravity in the 1600s. He invented calculus. And that was also that he could predict forces or motion. I think he's working on motion of orbiting stars and planets, and he invented calculus so he could do that better, which, again, unreal guy. And then another thing, though, was these three laws of motion that we're going to talk about today. And these things that I think now are sort of, they're just in our back, they're in our back of our mind. They're just true. We know them to be true. But, if you think back in these days, like take inertia. Inertia is Newton's first law. So an object in motion will stay in motion, and an object at rest will stay at rest unless acted upon by an outside force. And if you think in our actual experience, and certainly in Sir Isaac Newton's actual experience, that was absolutely not true. Maybe the object at rest will stay at rest unless there's an outside force, but there is no object that'll stay in motion forever without acting on it. And the reason, of course, we know is that friction. So if you say roll a ball down the hall, eventually it's going to come to a stop, right? And that's because there is an outside force, friction, acting on it. But to come up with the idea that, well, geez, if there was no force, if there was no friction, that ball would go forever. And that was the idea. That's sort of the really cool thing of inertia that Sir Isaac Newton realized, is that, take friction away, that ball goes forever. So some examples of Newton's first law, that we experience all the time, and I'm reading the green here. So we have to wear seatbelts. Why do we wear seatbelts? Because, when you hit the brakes on your car might stop, but unless there's something causing you to stop, you won't stop until you hit the windshield, and that would be the outside force. Car engineers would rather, it be your seatbelt act being the outside force. My similar story to that is my daughter and my pug and I were driving to a soccer game or something, and the pug was standing sort of, he had his feet in the back seat and his paws sort of right between my daughter and I, who's in the passenger seat. and I had to slam on the brakes because someone stopped in front of me, and Charlie sort of flew into the stereo, right? And that was my, I told my daughter, there you go. The car stopped, but Charlie didn't. Charlie flew until he hit the stereo, and then he cried and sat on her lap, and it was pretty pitiful. But so that's Newton's first law, of course. And another one, in the car that we experience, because it could be turning a corner. Because remember, uniform motion means a straight line. So you could maintain the same speed. But if you start negotiating a curve, you might notice yourself being pulled into the sort of pushed, like you're being pushed into the door. Well, you're not being pushed to the door. The door is pushing into you. And it's that's what's causing you to turn the corner. And actually the force between your butt and the like what's holding you on, for the friction basically holding you on the seat of your car. His second law of motion, I always call that the math law. It ends up with an equation. If you apply more force to an object, it will have more acceleration. If you apply the same amount of force to two objects, but one has more mass, the one with less mass will have more acceleration. So there's the equation that describes that. Force, F, equals mass times acceleration. And here's my example. Mr. Johnson standing still in the hall. You run as fast as you can into him, and he doesn't budge, right? Because your force is not enough to cause that big mass to move, or at least very little. Miss Hillary, tiny little Miss Hillary, standing there, and you run full throttle into her, and you can get her flying because she has less mass. She's a lot smaller than Mr. Johnson, right? So her less mass causes more acceleration for her. And another example with more force, more acceleration is if you swing sort of all your might and hit that baseball, you can get a home run. But if you just barely swing, hardly any force hits that ball, get a bunt. Okay, more force, more acceleration. And I think these are things that these are just very common things. Everybody knows this. If you push harder on something, it's going to move further. Duh. But Sir Isaac Newton put math to that, right? He made an equation out of it. And this equation governs the design of every piece of equipment that has ever been used. The third law, his third law of motion, is what I call the karma law. Do unto others as you'd have done to you. For every force, there's an equal and opposite reaction force. So examples of Newton's third law could be two ice skaters hold on to each other. Okay, here's our two ice skaters. Skater B, this little one, she pushes really hard onto skater A. And skater A will move a little bit, right? Because B is applying a force onto her, so she's going to move backwards, right? But at the same time, skater B is going to move backwards as well. And that's because even though she's not trying to, A is not trying to apply a force to B, just by virtue of B acting on A is acting on B. The other example would be walking around at night at home and you stub your toe. You're hitting, what is it on the chair leg? You're hitting the chair leg, but your toe hurts. That's because the chair leg hit you back. Okay, so equal and opposite forces. That's Newton's third law. And I think that's all I have to say about that. There's some great activities, and I'm gonna, I think in class I'll show some of my old videos of Newton's laws. And that's one of the things you have the choice to do, is make videos sort of examples of Newton's laws, and you'll see that up on the assignment page.